Okay, why do we need synthetic data synthetic data to work with? Well, many things. Software testing, for example, data manipulation, training artificial intelligence models, healthcare research because of sensitive data, financial research, and many other aspects. Types of data. When we talk about data, we have a lot of things to talk about. One of the first is how it is structured or non-structured. We have, for example, types of synthetic data that we can generate. Structured data. If you think about structured data, you recognize that is information that's organized according to a specific structure. Like, for example, customer records. A customer record is characterized by a few attributes, like name, age, address, purchase history, and many others. Also, transaction logs. You have timestamp, amount, direction, and description associated. Sensor readings, for example, simulated data from Internet of Things devices or wearables, for example, for health monitoring. Healthcare records, synthetic patient data, that it might include diagnosis, treatments, outcomes, and many others. So, how do we get there? We get there by using generation methods, and we have a lot of possibilities for generating data. Usually, we want to follow some statistical model. And I'm sorry if I say something not statistically formal or statistically correct. Nevertheless, if I do, please correct me. But what we want is usually to try to mimic some real-world phenomena. And these real-world phenomena can be, many times, modeled by statistical properties. And so we want to generate data that somehow follows this statistical model. In addition to this one, or in alternative to this one, we might also use rule-based generation. The rule-based generation allows us to put some conditions on how this data is generated. We'll see it better later. Or we can use I would say the modern type, which is to use machine learning, deep learning models for generating data. Like, for example, variational autoencoders or generative adversarial networks or others that are also here. So there are a lot of possibilities. In addition to structured data, we might also want to generate unstructured data, like images or audio files, including voice, text documents, or even video. And you know that today you have already many generative artificial intelligence tools available that you can use to generate any kind of these data. Even more, sequential data. Many data are always temporal pattern. And so we have samples that follow a specific period, seasonality, and we might want to work with it. And for that, we need to generate information that understands or that follows some temporal relationships. Most of the things obey some kind of ordering. And so this is also a huge area of development. So we already talked a little bit about this. Why do we need the synthetic data? Well, real data is difficult to come up with. And people that work in data science particularly feel this. And if we can control the amount of data that we need or have, even better. So we have no other choice but to generate it. In some technical aspects, we might need to balance the data. For example, we might have examples from one class that is very representative and examples of a different class that has very few examples, very few numbers. And so if we want to train a statistical model based on these, or even a machine learning model, it might not work well. It will be too much unbalanced. And so we need to find ways to balance the data set. Of course, you can tell me, okay, we'll eliminate the excess and use the same number in both. But sometimes to generate a good statistical model, we need a lot of it. And so it's better to have more than to have less. And for that, we can generate data. And of course, there's also the data privacy concerns. Some data is sensitive or has personal information. We cannot use it. Of course, you can anonymize it. Nevertheless, if we can have it free of any legal issue or problem, even better. So if we have the possibility to generate our own data, we can improve our machine learning models. We can even target some specific events like rare events or edge cases in training. We can reduce bias so that we can have better quality in data, or support transfer learning when we have real data. So I have synthetic, I produce my own model. Of course, it's biased towards the synthetic nature of my data, but I can train it or specialize it a little bit more when I have the real data available. Of course, if I have a means to generate data, it's cheaper than finding in the real world. So far, so good. Okay, first, for me, the easiest one, random data generation. So random data generation is probably the simplest method. And we generate data by random sampling. And how do we sample? Well, we specify a statistical distribution, and based on this distribution, we just collect data. This is fast and flexible, is not very costly, it doesn't consume many energy, and it's easy to implement. The problem with this is that typically is a little bit far from real world situations. Nevertheless, it's still useful for some use cases, like stress testing, edge cases, placeholders for the data, and so on. Do you have the slides?
Yes.
Okay. Probably when you see this slide, this provides a direct link to Google Colab. I think that to use Google Colab, you have to have a Gmail account. Nevertheless, all this code is available from download to your computer and work there. But it's easier if you just use the Colab. This approach for random data generation uses a library. It's a very, very simple library to use. It's called Faker. You can here. I usually use this in cybersecurity class. If they want to make some stress tests with data that simulates passwords or so on, it's very nice. User IDs, passwords, timestamps, log files. In cybersecurity, I use this a lot. Nevertheless, it can be used for generating a broad range of data. So if you don't know this library, look into it. It's very, very simple to use. And you'll see in just a few lines of code. It's very small, the font size, right? Better? Okay, by now I suppose that most of you understand Python language. Unfortunately, you're forced to learn it
Is available on.
No, only for the others. You came late, so. My pleasure in having you here. No, it is available. Just press the link on the slide and you jump immediately there. Okay. So after you can open the file, you can start executing it step by step. Everyone is used to Google Colab or Notebook. So no need to explain anything in this interface. All good? Perfect. Okay, so I'm installing the Faker library. Then the usual imports, NumPy, you know the NumPy library, pandas, and also the Faker. Perfect. Importing. Now, we initiate or we initialize the Faker library by creating this object. We might need, if we want to ensure reproducibility, we can specify seeds. This works with a random number generator. A random number generator in computers is not purely random. It is pseudo-random. And the numbers are generated according to an initial number, the seed. If we use the same number as seed, the sequence of numbers will be the same. And so I'm specifying the seed at any number so that all of us get the same results. If the seed is not initialized, we might get different results. Okay, just specify a constant, the number of records that I'm going to generate, the synthetic data structure. And so if you look at this and you have to guess, you can look on the left, the characteristic for each record. Customer ID, name, email, age, country, annual spend in United States dollars, and is subscribed. Now, if you look a little bit to the right, you see some code. And this code specifies the type of data for each record. For example, if you look here, state of country. So this state of country asks the Faker library to generate fake country names. We also have here fake name, fake email, and so all of these will be generated automatically by the Faker library. So it's easier for us. Of course, not everything is generated, or we don't need to call the Faker library. We have, for example, here calling the random function of NumPy to choose from true false with a little bit skewed distribution, 0.7 and 0.3. And so we specify the way we want to generate data like this. After this, we can visualize the data frame. So you see that is very easy to generate. And in a moment, I'm generating 100 records. So execute, here they are. If you look at this, all of this is synthetic. It's random generated. And it was, well, it happened very quickly. Look at the row number, the customer ID. By the way, the customer ID I forgot to mention, but if you look at the code, it starts with test, then 1000 plus I, where I is incrementing for each record. And so you have customer 1000, 1001, 1002, and so on, associated with the fake name, fake email, fake country, and everything that we specified above. So this is very powerful, very easy to use, just a few lines of code. Questions? After each example, you have available the code for the random data generation. After the other one, I have usually an example for you each one. The solutions are also online, but they are given. So try it at home. If you can't complete it, tell me and I'll share the solutions with you. Okay. Nevertheless, if you look at this, it's very similar to the previous one. We have 100 students, so it's not a customer. The types of attributes are a little bit different. Nevertheless, we have the name, fake name, age, random between 18 and 25. The course, random selection from a list, also we saw it before, and final grade, a float between 0 and 20. So we are generating the table. Now, the challenge is to use it. You already did something in Pandas, right? More or less. Okay, give it a try. Average grade per course, so you have to filter and calculate the average. Number of students per course, filter and count. Number of students who passed, filter and count as well. So, very easy. Try it at home, and then we'll talk. Nevertheless, if you want to explore in detail any of these, for me, it's fine. As I told you in the beginning, I'm a little bit I didn't make my mind about where should I lead. In the end, I have three deep learning methods for data generation. It's complex, but I would like you to have at least an idea about that. So if you want to explore this better, we can stop and go slowly. If you want to get an idea of the others, we can move. And then if we have time, we can come back to this. Nevertheless, I think that the example is there, you can try it, and it's very easy to achieve, I hope. Okay, next approach. Before we saw random data generation. Now let's move to make this random generation a little bit more close to real world example. And we can make this closer if we specify some rules. And what does this mean? Well, this means that I have to have some domain knowledge to specify this rule. And I can use this domain knowledge to generate data based on constraints. This allows us to have data that is more realistic or more adapted to specific context. Let's see how. So the code is very similar. It's a little bit more complex because in addition to the random generation, I'm going to add also some rules for it. And so the challenge is to generate employee records. And these employee records have some rules that we usually see in the real world, like, for example, the salary depends on the job title. Not everyone earns the same. Managers are usually older, so over 30 years old. I could only be twice manager. Employees in an engineering section have a different email. And so I can come up with the main rules and use them to make this data more specific for a context. So we are still going to use Faker. We are generating more or less the same that we generated before, but we are going to add some rules to it. Imports, the same as before. We might need to install Faker if it's not available. Of course. Sorry, guys, I forgot. Pip install faker. You have to add a new, I forgot to add this to the code. All good. Now we can go back to imports. Perfect. And now let's take a look at the code. Just like before, I'm initializing the faker library, also specifying the seed for the random generation. And now some of the roles. We have, for example, 4 roles: the intern, the engineer, the manager, and the director. The price range for each one is different. For example, intern earns 15,000 to 25,000. The engineer, 50,000 to 90,000, and so on and so on. So these will be used to generate data based on a rule. Departments, we have 4 departments: engineering, human resources, sales, and finance. Remember that one of the rule was people in the engineering department has a different email. And now I just need to implement the rules. And I'm going to encapsulate the rules in a function, in this case, generate employee. And the generate employee gets an employee ID, and then we are going to check if the rules apply, and according to this, return the proper value. For example, role is a random choice between a list. The salary range depends on the content of our list. So remember that the list is this one. And so we are going to assign an employee to one of these departments, one of these roles, randomly. This is where we do that. We are getting the salary for that role. And according to the salary, to the range, we are randomly picking a number. All good? Now, second rule, age. If it's intern, between 20 and 25. If it's a manager, between 30 and 50. Otherwise, between 25 and 60. So this is another rule. Department, random choice between departments. And remember, if he is from engineering, the email is different. The email should start with fake username, also generated by faker, and the prefix is engineeringdepartment.com. Otherwise, if it's from any other department, fake email. So it's if you remember from the previous example from the random generator, we didn't have any control. We just let it generate. We specify the structure. We specify the types of data that we want. We have an email, a country, a name, and so on. Here we have more control. And so we specify the rules. Usually the rules follow an if then else situation. So if condition, then action or result. Otherwise, the alternative. And then after applying the rules, I return the employee record. Executed, it is. So the ID is similar to before, starts with M instead of cust. 1001, 0002, and so on. Fake name, age. Remember, we have a rule for the age. Role, department, salary, and email. So we have rules for almost everything. Check, for example, Troy Hernandez, director, must be over 30. Confirm? Yes. Salary. I wish. Jessica, 22 years old, so younger. Salary. Also look for engineer, Melissa. 26. Okay. Okay. This is the role. This is the department. I was thinking that the role doesn't apply. Actually, it does. Make sense?
Can we pass representative the name of the person? If the name to use this name. Because for example, we have Jessica and then the investigations. There is a way to try to use the name to generate some information.
I don't think so. I really don't think so. Maybe if we specify the role, but I don't think that Baker allows to do that because the way it generates the fields are dependent one from another.
Can I ask you a question? Sorry. The seed, about the seed. What is the purpose of the seed?
The random generator in the deterministic machine, it's not real. It's simulated random. So it's not a pure random generator. And so we call it the pseudo-random generator. The pseudo-random generator usually uses the timestamp of the CPU to start generating numbers. If we want to make a situation reproducible, we have to ensure that the starting conditions for the generated randoms are the same. That's why I'm specifying the seed the same for everyone, so that you can have the same result.
Previously, you said that in order to get the same results or the same sequence, you are not getting the same sequence. So that's not where the seed works.
It works only on the random. Fake or faker might use different random generator than the one that we specified. As far as I know. You only make very difficult questions. Next time I'll bring a quantum computer so that I don't need to use the seed. Okay, homework. Very similar to before. We have some rules. You look, for example, the name is the same. We use faker. The role, random choice between several. The age. This is very similar to the one before. Yeah, it's the same. I get it. Nevertheless, you can try, because the interesting thing is what comes after, to use the data that was generated. Print a summary of how many employees fall within each role. Check if the manager and director are over 30 years old, and there should be none. Print salary range and so on, so that you can try to use the data. Questions? All good? The pace is okay, not too fast, not too slow? Nice. Let's make this thing even more complex. Simulation based. Okay, so before random and rule-based, we are generating data by sampling a statistical model. And in case of role, we specify some rules to make some restrictions on the data. Sometimes we might need data that it's very difficult to get from a statistical model. And for that, we can use a simulation. Maybe Anna knows more about this than me. Simulation. Nevertheless, what we want is to try to have a process that simulates some image. And this process tries to be as real as possible. So we are trying to model real-world processes that evolve over time. And this is usually applied to queues, events, or workflows. And it's very useful in many situations. So this simulation allows us to capture temporal dynamics and resource interactions. Is very good for some complex scenarios, like, for example, hospitals, factories, or even networks. And it's very useful for testing the performance of models, to identify where the bottlenecks are, or to check the overall system behavior. Of course, you can say that we could use analytical methods to get there. But the purpose of this is to get the data from it. And so let's let the system make the simulation and gather the data that we retrieve from it. Okay, simulation-based generator. You should also be able to click on the link. You'll get to this example. This example tries to simulate the patients going to a clinic. And so each event in the simulation will have a timestamp. And the events are associated with several things that usually happen, like patients arriving randomly. They are queuing for the available doctors, and then we have a treatment period per patient. If you look just at these three, you can realize that the dynamic is relatively complex. We can have one customer every 5 minutes, and then 5 appear, and then 1 hour without anyone showing up. We can have one doctor, 5 doctors, well, many things. And interactions between all of these is complex. What do we want? We want this simulation to generate a few pieces of information. Let's call, in this context, let's call it features. We are wanting the arrival time, the wait time, the treatment duration, with some other aspects. Use cases. When is this useful? Well, of course, queuing models in hospitals, traffic simulations, customer service call centers, logistics, and so on. For this, we are not using Faker. We are not generating fake data. We are simulating a process. And to simulate a process, there are many libraries that you can use for simulation, from the very basic to the very complex. And for this, I chose the simplest one that I know, that is the SimPy. SimPy is a library that has a simple concept, the concept of a process and event. Every entity in there is a process. The process is frozen until an event arrives. When the event arrives, the process wakes up, executes, and sleeps again. And so we can model the doctors, the patients, and so on with these processes and sleeping, not going to the hospital, waking up, going to the hospital, and get data from there. So let's try to see how it works. Of course, if we are going to use the SynPy library, we need to install it. And after installing it, importing it, you are going to see that it is also a very complicated code. Perfect. So the usual imports, the SynPy, the random, and the pandas, specify the seed. Okay, parameters. These are the, let's call it the simulation hyperparameters. We want number of patients of 50. We want the arrival time to be between 3 and 10 minutes. We can change this, of course. And the treatment time to be between 5 and 20 minutes. Then we specify an array, Python list, to store the records that are retrieved from the simulation. Now, I'm encapsulating the generation of the patient in a single function. If you look at this function, we have several parameters: the env, the name, doctor, and records. Some of these variables are input, some are output as well. The most important lines, so that we don't go with too much details, is this. So this is one parameter that we want to get, the arrival time, and check that we are getting the arrival time from the environment. We are not getting it from the computer. Remember, the environment is where the simulation is running. And I want the simulation time, not the computer time. Then, with doctor request is an event. So when the doctor process launches an event, then the doctor will wait. This yield freezes the doctor, and we start checking the wait time. Then we compute the treatment duration. Remember, it's between 5 and 15 minutes? Yes. And then we stop the patient until the treatment is over. When the treatment is over, then we specify the record. And in the record, we have the information that we want. The name of the patient, when he arrived, how much if he waited, when the treatment started, when the treatment ended, and what was the duration. And so this is the information that we are getting from the simulation. This function is called from this one. Of course, I don't want one patient. I want 50 patients. And so I have here a cycle that goes from 0 to 50. And for each one, freezes and launches the patient. So what is this doing is calling 50 times that function. In that function, we have some parameters. The parameters are specified in association with the environment. So we initialize the environment in SynPy. We specify the resources we have available that we want available in the environment, in this case, 2 doctors. And we start the process. The process calls the patient generator, that in turn calls 50 patients. And they start interacting based on these random assumptions. When we execute it, they will be stored in the records. We create a data frame and we print it. See how fast it was? This is why it is important to use the environment time, not computer time. We don't want to wait 3 minutes per patient. And the simulation happened very quickly. And if you look at this, patient one, arrival time 4, 0 minutes waiting. So the resource was 3 treatment and so on. Patient 2, we have 2 doctors. 0. Patient 3 had to wait because they were busy, and so on and so on. And so when we simulate this, we can get some interesting information about how the process interacts. This is a little bit more difficult than the Faker library. You have to think about the entities, the resource, and the processes, and what kind of information that you want to get from it. Nevertheless, the SimPy library has a lot of examples there. It's very introductory, so it's very easy to understand. Any questions so far? Of course, you have homework. And I know that all of us like to go to the bar, especially at 11 and at 4. And so to calculate better the time to go to the bar, you have a challenge. We have a single guide, yeah, and 30 customers going to the bar and following those
the time work, for example, in the situation of the or in the other example, so sometimes the time, the treatment time is depending on the disease of each person.
Yes.
Okay, we can also introduce
We can.
variable.
Yes, to make a condition on that. Yeah, and if you look at this, the wait time is random. Well, the wait time depends, but the treatment duration depends on this. And so the treatment duration is just a random sample between the treatment time, that it's between 5 and 20 minutes. If we add a rule there, we can choose from a list, assign the disease according to a distribution, and the treatment according to each of the disease. Nice. I like it. What do you think?
So because we are also using the simulation models.
Yes.
Anything like master data.
It's related to this. Okay, come. Go ahead. Now, sometimes it's interesting. I did many years ago a simulator for measuring to get data from the loneliness of people as grow older, and it's related to the social connections. And the process was increasing the year, the probability of dying when someone dies, the social link breaks. And it was interesting to map some social situations with a simulation. Questions? Okay, now comes the worst part. Let's see if you can take it. If not, please scream very loud. Generative models. So, I suppose by now everyone knows a little bit about machine learning, right? And so what the generative models are, or at least how do we see them in this context, is some form of machine learning, which means that we are going to need to train some of these models to generate data. This is a little bit strange because, wait, I want to generate data, but for generating data, I need data. So how does it work? And so these are special situations. And are only valid if I want to generate something with that we already have, but with much more with different uses and with a bigger number of examples. Okay, why I'm talking about this? We saw that we have the possibility for the random generator, rule-based generator, simulation generator, but there are situations that might fall outside of these possibilities. And for that, we need to capture some difficult relations between data or related to the structure of the data itself. Nevertheless, if you look at the scientific literature, even in the social media and so on, there are a lot of information about generative models. And in particular, all of these that rely on deep learning architectures. We have more data, we have more computational power, we have better deep learning algorithms. And all of these is coming together in bigger models, more able, and even with the possibility to generate very realistic data. Do you know this person is not real website? Oh. Or this person does not exist. So if you're curious, there's a website, the title of the website is "This person does not exist.com." If you go there and refresh the page, you'll see all the time different faces. And all of these faces are generated, so they don't exist. And if you look at this, it's almost new. And of course, this cannot be generated by random generator, rule-based or simulation. So we need to go to different forms for generating data. So, trends. We have the possibility to deal with high-dimensional data. We have the possibility to deal with very complex data, and even with the possibility to deal with correlated data. We have the possibility to generate realistic synthetic data like you saw before. This person does not exist, for diverse use cases, like fake passports and so on, only legal applications. The applications, data mutation, missing data, generating missing data, fairness improvement in biased data sets. So if we have individuals that are not represented in a specific data set, we have the possibility to generate, to compensate for that. And of course, privacy preserving data sharing. There are three main deep learning approaches for generative methods. I was expecting, it was expected last week to talk about autoencoders. And so this is a little bit short. I'm just going to explain more or less the gist of it, what they are and how they work, and how they can be used for generating data. Okay, autoencoders. Before we get into what it is and how does it look like, I suggest you to think about autoencoders as a way to compress data. like the zip utility. You have a large file, you zip, and it uses less space. Of course, you can then get back the original data by unzipping the archive. In the case of autoencoder, this is a lossy operation. We compress it, but we lose information. When we get it back, it will be similar. Not the same, it will be similar as the original data. And this gives us very interesting applications. Like, for example, removing noise. Who sees those TV shows related to crime scene investigation? Everyone sees, you see a picture of a guy, you look at the face and then you don't recognize, and then they press a button and the face appears crystal clear. Also the license plate. You see a blurred license plate, press a button, and then the license plate appears so that you can read it. Okay. Removing the noise from the data set. All of this is noise that you can use on the encoder to improve. Also, the opposite. If we have a data set that has a lot of features, and I don't know, 2,000, 5,000 features, we can make a representation of the data with much lower dimensionality. And then use simple models for classification, regression, or whatever. So, autoencoder is all about compressing. In the autoencoder architecture, compressing means encoding. So we have data, we pass it through the autoencoder, and we want to get a code that represents that data. Encoding in this context, as I told you, represents compressing the data or reducing the amount of memory necessary to store it. Now, I think Anna spoke about unstructured, unsupervised learning, clustering, right? So this is also another form of unsupervised learning. In unsupervised learning, we don't have the label. We have the data, and we run an algorithm on that data. So autoencoder is trained by the same approach. We have the data, and it trains on that data without looking at the labels. We use backpropagation to train, adjusting the weights. We are going to look a little bit better about that. And we are going to use it to make a smaller representation of the original data. And then potentially we can reconstruct it, or at least try to get something that looks like the original data. How does it work? Well, it looks like a bottleneck. We have big, small, big. The input is here, and the big. Where is the compression? There. So we have, for example, n features that are compressed into n features. Of course, it's compressed because I have less number of neurons in the middle. Perfect. Why do we need the rest? Why do we need this part of training? What we want is to have data here and then the same data there. And we compare it. If it is not the same, the error is high. If it is the same, the error is low. And based on the error, calculate gradients, adjust the weights, and gradients. This is interesting because it allows us to do many magic things, especially in images. Like, for example, coloring images. We can have a black and white image in the input and get a colored image in the middle. depending on the representation that I want. But more, we can have feature extraction. In the feature extraction, we can select the features based on what we want. In this case, we want to take out artifacts, remove artifacts. If you look at this image was captured with a flash. There's something that is reading my image, and also it's skewed. So it's not perfectly aligned. And so I can use the autoencoder to get a better version of the original. This is very interesting. We are going to explore this a little bit better. But this is converted into another dimensional space. You have here n dimensions. You have here m dimensions. And so you have a function that maps from n to m. Okay? All more or less good. And then we have a different function here that makes the reverse. Maps from the n to the m. So we lose information from here to here, and we gain information from here to here. Fortunately, the information we lose here is the bad one. That flash and that skew. Okay? You can ask me how. Yes, that's the question. Sorry. With the training. With the training, we give it good images. And it learns to represent good images there. Of course, this is so short that is the concept of a good image. It's not the good image itself. When I put the bad image, it tries to map, to find the good image that it knows about. And then use the abstract representation of the good image to generate a new one. Looks easy, right? Okay? But there are more. We can reduce the image and we can also expand the image from a big image to a small space, but we can also go to hyper resolution, like, for example, the CSI example. Remove noise. This is like a low pass filter. We have noise in the image. If we train the autoencoder with good images without noise, it will learn the representation only of the good images. Bad images doesn't know what to do with it. And so it will reconstruct based on the main concept of the image. Of course, if I ask you what is this number, you can recognize it, right? A 2. But if I ask you, do you really see a 2 there? No. I see something that looks like a 2 with dots. So it's more or less the same thing. You know by context that it is a 2. And the autoencoder learns the context and tries to map it to the context it knows. More interesting things. Watermark remover. So we train good images, everything that's not good gets stripped away. I know it's more or less magic. Before I showed you an autoencoder with neurons, this one. Okay, you look that we have a peak, the input, then a bottleneck, and then expands again. And this is built with an artificial neural network. Not going into the details of this. Nevertheless, in machine learning, there is another type of neural networks that we call convolution neural networks. The convolution neural networks use usually inspiration of how our eyes work. And our eyes, our optical system works by sections. Probably you didn't think about this before, but our attention goes to the high contrast area. The high contrast is where we have the swift changes in color or light intensity. For example, you look at the face of a person and you immediately see brighter part, darker part, and so on. And so based on these transitions, you can recognize complex features like a face. The convolutional networks work like that. They try to find contrast areas and they work in different responsibilities with increasing abstraction level. For example, this one will look for straight contrasts, lines. This one will look for sets of lines, which includes the curves. This one looks for arrangements of those shapes. And the last one looks at faces. This is very powerful. The power of these kind of architectures was demonstrated in 2012 when an algorithm based on this exceeded the human skill in identifying objects. So in this competition, the human was able to guess correctly 95 point something% of the time. And for the same time, for the first time, the computer vision algorithm exceeded that with 96.1% getting right. Now it's close to 99%. So even better than humans. So it works very well. And this kind of architecture uses a different operation than the traditional neural network. But we can use it also to make an autoencoder. We have big image, small image, and big image. And you ask me, wait, how can I have the information of many big images here? If you look, the length of the boxes are different. This box is thin. This box is short, but wide. And this is the dimension of the image. Here is a color image, red, green, and blue, 3 channels. Here is no longer an image. It is a collection of features. And here maybe 60, 70 layers in the same image. So I'm losing width and height, but I'm gaining depth. And this way, I'm able to capture the concepts of the image instead of the image itself. More or less. Conceptually, okay. Worst part. Autoencoders are deterministic, meaning that you show an image, it converts the image to the same point in the other space. You get that point and you can convert it back to the same image. So perfectly deterministic. This is a problem because it's not flexible. If you have this and this, you know that's a 2. This is a 2, this is a 2. But the concept is the same. The data is different. And so if the autoencoder is deterministic, this means that it's more difficult to recognize these two as the same concept. If it's non-deterministic, I can make it a little bit more flexible in the interpretation of the abstract. What does it mean to make it non-deterministic? Well, it allows us to introduce something that relies on probabilities. And this is called the variational autoencoder. The principle is the same, but the deterministic ones make the representation of the input like this, starting from 0 and going gradually up. So this is what we see in the middle of the autoencoder. Each of these points is one image. In this case, it's one digit. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 again. So each one of the color is a different number. You see that far is okay, but here it's very confusing. And this means that the images that are here are easily mistaken. So it's difficult for the autoencoder to generalize the concept. And so the variational autoencoder, instead of having the deterministic approach, calculates two parameters, the mean and the variance. And the mean and the variance are placed in that bottleneck. And so when we put an image, it calculates the probability of being in that place, not in that place itself. And this allows us, you can see here, compute spreads, compute averages or means, and this allows us to have something a little bit better. So instead of going gradually from here, they are starting to cluster together. And so it becomes more flexible. And this is the most useful for data generation. How can we generate images without encoders? We have the autoencoder like this. This is encoder, this is decoder, and this is the latent space. In the training, we put the image here. We get an idea of the image there. We compare it. If they are equal, good, or similar. If they are not, wrong. And so we need to learn it. And so after training, we'll get there a representation of the image. So how can we use this for image generation? We set a number there. If we set a number there, we are stimulating the latent space. And the decoder will use that number to generate an image. And so I'm stimulating the abstract representation of the image. Like the horse is number 57. So 57, horse. And now the giraffe is number 59. 59, giraffe. Okay, and 58. Donkey, for example. How? Because they are similar, and so they are clustered together. If I stimulate these points, I'm generating the images. And remember that I'm just stimulating the concept. This is used only for training. I remove it later, and I use only the decoder part. Make sense? More or less. Tell me, sleeping already?
Good. To train, you will have to have a very good example of the model there. Do you have an idea of how many images you need? And the diversity of the image. Do you have any kind of numbers?
Now I'm going to be a politician and say, it depends. No, it's very sensible and sensitive to all of that. I need to have a very good model. So the number of parameters, number of layers, the dimension of this latent representation, dimension of that is very important. And also very important, the number of data, the amount of data, and the quality of data.
We are always talking about thousands, right? Or
At least.
okay.
At least.
That's the minimum, right?
Yeah, I trained one autoencoder with a little bit over than 1,000, and it worked more or less. I trained one, you have it in the example here, with 89,000, and it worked relatively well, but 89,000 images. So it's not 100, even 100 is too much. So 89,000. The convolutional neural network that I talked about before, the one that exceeded human skill, was trained with 1 million images. And so it's absurd amount of data. More questions? Okay. Of course, the code is more complex. In Colab, I have only the second part. I don't have the training part, at least if you click on this link. Actually, this is the data set. But all the code is there, so you can look at how an encoder looks like. I'm going to show you here in my computer, then you can explore it later. This code is in PyTorch. Is a little bit more demanding, but it's not so difficult to understand. In PyTorch, we have the possibility to specify a neural network. In this case, we are going to specify a convolutional neural network, the second one that I showed. And so, what we have here is a sequence of convolution layers with normalization and activation function. This happens 5 times. And if you look there, hidden dimensions, 32, 64, 128, 2056, and 512, that is the width of the boxes. So we start with one box with 32 deep, then 64, 128, until 512. And we have first the encoder, then we have the decoder. In the middle, we have variational autoencoder, the spread, the variance, and the mean. Yes, deep breath. Okay, it's not so difficult. Nevertheless, of course, is more if we want to capture the high-dimensional data and the concepts. Of course, we need a lot more. But let's see how it works, and it's really more complex. Okay, I struggled a lot to find an interesting data set. This is image-based. We can use the same for other types of data, music, audio, text, even temporal data. For this, I used image. I'm not sure if I'm going to follow this step by step with you. We need models, we need other libraries. And the way I'm doing it in Colab is to map my Google Drive. So we need to have a storage space. And so it is to connect the Colab to the Google Drive. In the Google Drive, you have to create this folder, synthetic. After you create synthetic in Google Drive, it should work well. To download it, you have to install Kaggle Hub, is a library to access it. After installing it, the usual imports. And we are going to use images. To use images, usually we transform how the images look like. You know how an image is represented in a computer? Is a matrix. If it is black and white, each position of the 2D matrix has a number, usually from 0 to 255, where the number specifies the level of gray from white to black. If it is red, green, and blue, if it is a color image, we have a 3D matrix with the red, green, and blue components here. And so this is the image representation in a computer. Of course, we usually don't make algebraical operations directly in images. We do it in matrices. And we are going to transform the image representation into a tensor, a matrix that can be computed in a GPU, CPU, tensor processing unit, or others. And so the transformation is that. And I'm going to normalize the image. You see that from 0 to 255, the next transform is to normalize it with a mean of 0.5 and a variation of 0.5. And so all the numbers will be between 0 and 1. With some exceptions, of course. Now, these two classes are made by me. It's in the code that you can find and install in your computer, and allows us to encapsulate the data set. So executing, perfect, and this particular data set has 8,000 images. And the result is very blurry. This is the data set. So it's a data set I like to use because it's cute. It's short, each image is 16 by 16, so it's very quick to process, more or less. And we have 5 classes, 5 different classes of objects. Side-facing, cube, side-facing also, where is it? All of these are side-facing. I filtered to use the 8,000 examples for the side-facing. So what I'm going to do is to train an autoencoder with these images so that I can have a representation of the side-facing pixel art. After that, I can stimulate the autoencoder to generate new side-facing pixel art characters. Okay? So this is the introduction to the data set. Now we can take a look at it here. The autoencoder. So going a little bit quick, importing. Now, the autoencoder is a neural network. The neural network has a lot of parameters inside. These parameters are usually stored for later use. You can see here are stored parameters. When you mount the folder in Colab, this file will be there and you can use it directly. This was trained beforehand. By the way, to train this autoencoder took in my computer with the GPU 40 minutes, more or less. So it's reasonable. Okay. I can't show you. But it should, perfect. Okay, This is the original image. This is the generated image. You see that they are similar, although it's a bit different. Why do I have the original image here? As I told you, if I want to use the autoencoder to generate images, I have to stimulate the latent representation. But I don't know what it is. So here it's 128 dimensional space. And so it's a vector with 128 parameters. So I can guess, but I didn't want to guess. So what I did is get the real image, pass it in the encoder, get the representation, and put the representation back to generate the image. And you can see it, that more or less the autoencoder worked well. So from the real image, compress it, decompress it to the fake image. Of course, it's similar. It's not exactly the same. Questions? You're going to die today. Okay, you have the code here. You can try it. I tested multiple times. It worked well. But if you have any difficulty, anytime, tell me. Okay? We're not going to diffusion. Just talking about this problem. And just an idea about the diffusion method. Any questions so far? Okay, next technique, generative adversarial networks. Actually, this term does not represent a network, although it's called generative adversarial networks. It represents how to train two networks. And these two networks are trained in opposition. Maybe it's better if you look at this image. So this image represents fake money factory. In the fake money factory, we have two roles. We have the faker, so the people that makes fake money, and we have the quality control, the guy that looks at the bills and says, okay, this is real or this is fake. And so we have two different networks that we want to train together, and we want them to improve together. The better the faker becomes, the more difficult for the quality control to identify fake bills. In the end, the fake bills will look real. And this is what we want to generate new images, for example, or to generate new data. And so we have real data here, and we have fake data here. We mix it together, and then we have somebody classifying it as fake or classifying it as real. If he gets it right, the faker must improve. If he gets it wrong, quality control needs to improve. And so we are training in turns. Okay? And so it will be something like this. Image of a real bill. We give it to the discriminator. This is the one that will try to classify it as fake or not. And so if the prediction is real and the label is real, perfect. I am perfect. I don't need to train. On the other hand, if the label does not match, so you didn't recognize it correctly, so improve. On the other side, we have the generator, and the generator uses random numbers as input and generates fake data based on those random numbers. And this fake data is given to the discriminator. If the discriminator gets it wrong, has to learn a little bit better. If gets it right, then it's the generator that must improve. And so it will be like cat and dog. And both will improve over time. And Anna, this is much more difficult to train than the autoencoder. It takes longer. And for example, the autoencoder I trained with 50 epochs. These I trained with the 2000 epochs. And so it took almost 8 hours on my computer to train. And the result is worse than the autoencoder. There's another aspect. So you also have the code in Collab. Just going to show you the aspect. So the same data set, but different generating method. So you see more or less, you recognize some pixel art, of course, with some difficulties. Nevertheless, it's there. Of course, in generating, we don't need a discriminator. The discriminator is only used for training. After that, we remove the discriminator, we keep only the faker, the generator part of the network. Okay? Well, since we got here, let's look very briefly to diffusion models. The diffusion models are the most capable, are the ones that generate the best images in generative models. You know, the DALI and the others for image generation are all of them, or most of them, are based on diffusion models. Diffusion models are based on a physical principle. And the purpose is to systematically destroy data. Wait, it is not to generate. So why do we need to generate data? Well, if you learn how to destroy it, we learn how to get it back again. So you can think about a glass of water and you drop ink in it. In the beginning, the ink is concentrated in a single point. After a while, it starts to spread until it fills the whole surface of the water. And so the diffusion models work on this principle. We have an image and we want to destroy the image until we don't see the water any longer. In this case, the image. And of course, if we want to generate image, we have 2 steps. First, destroy, and then get back, reconstruct. And so we have the forward diffusion and reverse diffusion. And this is the principle. The interesting thing about this is that the forward converts the image into noise, and the reverse builds noise into image. And this is interesting, because if we start with a good image, we want, as a result, that thing on the right. So pure noise. And it was completely destroyed. This is the forward diffusion process. How does it work? Well, time 0, it's an interactive process. In time 0, we have the image. We generate random noise. We add it together. When we add it together, we start to see some expression of the noise in the image and move it to the input. We generate more noise, add it, and go back to the beginning. Generate more noise, add it, and so on, until our image gets obfuscated by the noise that we are having. And see that in the GAN and in the autoencoder, everything happens in one time. Input, output. Here, the diffusion process is really like dropping ink, and it starts to spread. So I drop a noise, and then interactively destroy the image more and more. Not going to bother you with the mathematics, but what we are doing is just start with the image and add noise that follows around the distribution. What's important here is this BT. This BT is called the scheduler. And the scheduler gives us the amount of noise we have per timestamp. For example, in 220 timestamps, this is the linear scheduler. So I'm destroying the image, and more or less from the middle, it starts to be almost unrecognizable. There's a lot of recommendations in the literature regarding the scheduler. And another possibility is the cosine scheduler. The cosine scheduler changes a little bit the way the noise is added. You look at the image is recognizable almost up to the end. Only here is unrecognized. So this is the comparison between the two. This gives better results than this one. Nevertheless, the purpose is the same, destroy the image. But if we delay the destruction of the image, the model learns better. We get better results. And so the cosine is better. Okay, it's easy to destroy. Just add noise. How do we get back? How do we reverse the diffusion process? Well, we train a network. And we train the network to predict not the image, but to predict the noise that you need to remove. And so instead of predicting the image, we predict, okay, I have a lot of noise. What can I take from this so that the image starts to appear? Interesting, right? Remember GANs? GANs does it in the same step. And it's very difficult to train, I told you before. In the diffusion, this is more step by step. You can look at this as a Markovian process, only not, because the transition are dependent. And so we start with noise, and we interactively change states until we get the reconstructed image. How do we change states? Well, we have to train a neural network for that. And for training a neural network, we use something like an autoencoder, a representation inside. But we are going to see better what is really used. So that is the image, the destroyed image. And we want interactively to remove noise. And so what the network is calculating is the noise that we can remove from that one so that we get better image. And so we remove it and we put it again in the entrance. It calculates the noise to remove. We removed it and get it back there. Calculates the noise to remove it, and gets back, and so on, until hopefully, after a few interactions, we get the clear and clean image by removing noise that was predicted by the network. How does it work? Well, I'm not sure I want to bother with all of these details, but I just want to focus on one thing. So I'm going to jump this part. Remember this image? It's like an autoencoder, right? So we have big, bottleneck, and big. There is one difference. We have connections that goes from the beginning to the end, and so on and so on. So if we change a little bit this representation, it looks like a U. And this is called a U-net. The interesting thing about this net, this was first proposed in 2015, and it was very good for image segmentation. So recognize people or birds or objects in images. And people realized that this is very interesting because I have not only the connection to high-dimensional space, but also connections to low-dimensional space. And it makes it more complete. But the most interesting thing is I add two things more. Remember that this is an interactive process, time 0, time 1, time 2, time 3. And so it's time dependent. If it's time dependent, I have to add a time embedding. And so I'm adding a new vector. And this vector represents the time step. But the most interesting thing is this, the context. And the context is the description of the image, like person on the horse. And so this describes the image. A light bulb, an apple tree, or so on. And so the context is added there, actually it's multiplied, and somehow it changes the abstract representation inside. And so I can use this as a prompt in the image generation. This was just what I wanted to get to. Okay, you have this code there with the labels. In this one, it was trained with almost 100,000 images in 5 classes. So you can ask for human character, side character, food, weapon, or you can ask for 0.5 food and 0.5 weapon. So you can merge together the labels and generate something different. I can show you how it works. Just for finishing, where is it? Diffusion generator. Of course, it's a little bit more complex. Because of the interaction process. And you see here are the labels. Human, human, side-facing, non-human, non-human. Food, food is the label that I'm going to try to generate. And so interactively, it is changing calculating the noise to remove, and you get, well, relatively good results comparing to the autoencoder. Side-facing, front-facing, side-facing, and this starts to blur the weapons, the food, and so on. It's a little bit unrecognized. And this is because the representation in the data set is lower. So I have lower. And then I can start mixing things. For example, a full human also looking like 60% food. Or this one, 60% food, 40% spell. And so I'm changing the labels to create different things. This one, I don't know if it is a weapon or a tool. Well, it depends on the training process. Okay, I hope that you have the first part, you have very useful things for data simulation, random role simulation based. We also have some concepts about generative models, how the encoder can find them.